Let's talk about what our genes can tell us about ADHD, ADHD symptoms, and common comorbidities. If you're like me and identify as neurodivergent and experience ADHD symptoms, or you've been formally diagnosed with ADHD, you may have wondered why some of us seem wired so differently. When it comes to understanding ADHD, psychology often uses a top-down approach, looking at symptoms and seeing how they fit into diagnostic criteria like the DSM-V. Neuroscience, on the other hand, takes a bottom-up approach, focusing on what's happening in the brain, such as neurotransmitter imbalances or gene expressions. Knowing your genetic profile can provide insight into why you experience certain symptoms and how you might respond to those interventions. For example, someone with the MTHFR variant might benefit from tailored nutritional support to optimize methylation. We'll talk about that more in just a minute. Genetics plays a big role, but understanding it can be overwhelming. So today, we'll break it all down, from what your genes say about ADHD to how they relate to clinical and subclinical conditions. ADHD is a complex condition influenced by both genetics and environment. It's not caused by a single gene, but by a combination of genes that affect brain chemistry and function. Think of it like baking a cake. Each gene is an ingredient, and together they create the final result. But here's the catch. Some genes are like sugar, playing a big role, while others are like a pinch of salt, contributing only a little. ADHD is polygenic, meaning multiple genes contribute to symptoms. Even genes involved in metabolism and methylation, like MTHFR, can play a part, and these genes don't act alone. They interact with environmental factors like diet, sleep, and stress. The MTHFR gene is often discussed in ADHD research. It affects how your body processes folate and supports methylation, a process critical for producing neurotransmitters like dopamine, norepinephrine or noradrenaline, and serotonin. There are two key MTHFR variants to know. Firstly, the C677T variant. Around 30 to 50% of people with ADHD have this polymorphism. Of those with the C677T homozygous variant, 30 to 50% experience clinical ADHD, and another 20 to 40% may experience subclinical ADHD symptoms. This variant is associated with a higher likelihood of other conditions such as anxiety, depression, bipolar disorder, and ASD or autism spectrum disorder. The C677T variant can affect how your brain regulates mood and focus, and it may lead to more difficulty in processing emotions and social situations. Secondly, the A1298C variant. This variant is less directly associated with ADHD, but still plays a role in related conditions like anxiety and depression. When combined with the C677T variant in what is referred to as a compound heterozygous state, it may increase the likelihood of experiencing ADHD symptoms or other mental health challenges. Both variants can contribute to impaired methylation, which affects the brain's ability to regulate mood and focus, but the effects often depend on whether the variants are homozygous, heterozygous, or combined. It's not just MTHFR though. Other genes play significant roles as well. DRD4 and DAT1 impact dopamine signaling, often linked to impulsivity and reward sensitivity, key features of ADHD. COMT is another important gene in ADHD research. It stands for catechol-methyltransferase and affects how quickly dopamine, norepinephrine or noradrenaline, and other neurotransmitters are cleared from the brain. The MET variant is linked to slower clearance of dopamine, which can make people highly sensitive to emotional stress and conflict. However, it also tends to improve cognitive performance in high-pressure situations. The VAL variant, on the other hand, clears dopamine more quickly, which can reduce emotional sensitivity, but may lead to challenges with sustained attention, especially in low-stimulus environments. Both variants can contribute to ADHD symptoms, but how they manifest often depends on the individual's environment and stress levels. SLC6A2 also affects norepinephrine or noradrenaline transport, playing a role in attention and executive function. Some genes are more likely to influence ADHD symptoms in childhood, like DRD4 and DAT1, while others, like COMT and MTHFR, may contribute to symptoms that persist or emerge in adulthood. This might explain why ADHD can look different across the lifespan for different people. Genes aren't destiny. They're just one part of a complex system that includes environment, habits, and choices. Understanding the genetic factors behind ADHD and its symptoms can feel empowering. It's not about labeling yourself, but about gaining insights that can guide your journey. Whether your challenges are clinical or subclinical, knowing what's happening beneath the surface can help you take steps towards better mental health and well-being. If you found this video helpful, I'd love to hear your thoughts. Let's keep the conversation going about how genetics and neuroscience can help us better understand ADHD, neurodivergence, and its symptoms.